Welcome to DriverDTrains. Thanks for stopping by. I'm your host, DriverD. Our conductor and brakeman, Scratchy-C, is taking the day off. In my last two videos, we looked at how to assemble and configure a WiTController to control our trains with DCC-EX, JMRI, or any other command station that supports the Throttle protocol. In this video, we'll celebrate open source projects and assemble another WiTController using different hardware. Be sure to check this video's description for links to my other videos, as well as the various websites and products I mention here. Also, if you are enjoying the videos, please leave a comment and hit the like button. And if you haven't already, be sure to subscribe to the channel. We're shuffling around the yard today, so let's enjoy the moment while we can. WiTController for DCC-EX, Take 2. Here are all the spotting locations and our dance partners for today. First, we'll assemble a new version of the WiTController using different hardware than before. Then we'll look at how to configure the code for our new WiTController using the Arduino IDE. After that, we'll run some trains. We've got our dance card, so let's start this shuffle. WiTController for DCC-EX, Take 2. Part 1. Assemble a new WiTController. In my video number 9A, Assemble a WiTController for DCC-EX, we assembled a WiTController to control our trains. The WiTController is an open source wireless throttle and controller created by Peter Akers from Queensland, Australia, that we can use to control our trains and layouts. The WiTController works with DCC-EX, JMRI, or any other system that features a Throttle server. One of our subscribers, Clinchfield Model Railroad, recently posted a video here on YouTube demonstrating how he connected a WiTController to his ESU ECOS command station. Be sure to check it out.
And there you go. See my locomotive's headed out.
The wonderful thing about open source projects is that we can freely modify and customize them to suit our own needs and likes. While searching for parts for the first version of my WiTController, I found some alternatives that I thought would make an interesting take on the WiTController, different from what I originally had in mind. The inspiration for this alternative WiTController started when I found this combination OLED display and rotary encoder board on Amazon. In addition to the display and rotary encoder, the board also features two additional push buttons. I liked its compact form factor and the fact that connecting all these components to the ESP32 would require only 9 wires instead of 13. A single version of the board is available for $10, and a 2-pack is available for $17. I'll include links to all the parts I used in this video's description. The next item that I came across while searching for keypads was this compact 4x4 16-key matrix development board with pre-attached right-angle header pins. It occurred to me that I could put the keyboard and the display encoder combo boards side by side with a battery and the ESP32 WeMOS Lite development board underneath and have a reasonably compact WiTController. If my original WiTController resembled an iPhone, this version would look more like one of those candy bar phones that were popular for a few years around the year 2000. As before, I assembled a prototype version on the breadboard to work out any kinks. I also took this time to install and configure the WiTController code, but we'll look at that process later in the video. Then I worked on designing a 3D printed case to put it all in. I thought about soldering wires directly to the various component boards to keep the size down, but eventually decided to use header pins for ease of assembly and later modifications. I also swapped out the right angle header pins on the keypad for straight pins. Maybe when I learn how to use KiCad or Easy EDA, I'll design a PCB to mount everything on. Then maybe I can get JLPCB or PCBWay to sponsor these videos. I worked through multiple iterations of the new design and made some simple buttons that just sit in place, sandwiched between the circuit boards and the top of the case. Because we are not constrained by the keypad, we can design and arrange the keys on the buttons however we like. For example, I moved the 0 key to the upper left corner of the keypad and moved the pound hashtag key to the lower right. I also printed the keys for the buttons in different colors based on what they do. For example, I made the keys that operate lighting functions yellow and the keys that operate the brake and stop functions red. I added a 3.7 volt lithium polymer LiPo battery, a power switch, and voltage divider resistors. For the battery, I used a 1200 mAh battery that has the same footprint as the one I used in my original WiTController, but lasts much, much longer. I'm very happy with the new battery and plan to replace the battery in my original controller with this new, larger capacity one. I soldered leads for a new battery connector to the back of the JST connector on the ESP32 board so that I can mount it right up against the side of the case. This makes it easier to insert a USB cable to charge the battery and program the ESP32 after the case is assembled. Everything just press fits into the case. First, the keys for the buttons go in the top cover. Then the OLED display encoder combo board and the keypad fit in. Next, there is a middle tray on which sit the ESP32 development board and battery. Then we can connect all the wiring based on the same wiring diagrams that we used before. For the keypad, the R1 through R4 pins for the 4 rows map to pins 19, 18, 17, and 16 on the ESP32, while the C1 through C4 pins for the columns map to pins 4, 0, 2, and 33. For the encoder, the SDA and SCL pins map to pins 23 and 22 as before, and the encoder push button goes to pin 13 as before. And the ground and VCC pins connect to the ground and 3.3 volt pins on the ESP32. The TRA pin maps to ESP32 pin 14, while the TRB pin maps to pin 12. For the 2 additional confirm and back buttons, we can use any of the available pins set aside for the WiTController's optional buttons. I selected pins 26 and 27. We can then wire up the battery to the JST connector and install a switch on the positive lead. If we want to see the battery remaining percentage indicated on the WiTController screen, we can add a pair of optional voltage divider resistors across the battery leads and connect their common lead to pin 34. Finally, I bent the header pins on the ESP32 over about 60 degrees so that I can make the case a little bit shorter. I installed the power switch into the side of the bottom of the case, connected it up, and carefully routed all the wiring so that I could slide the top and bottom of the case together. Once in the case, the encoder knob bottoms out when pressing the shaft to activate the encoder button, so we need to add a small spacer to drop down inside the knob so that it presses down on the shaft. I 3D printed a small disc for this, but almost anything will do. And with that, our new candy bar WiTController is assembled. Next, let's look at how to configure our new WiTController to run our trains. Part 2. Configure our new WiTController. Now that we've assembled our WiTController, let's configure the code to use our new hardware. As a reminder, we should do this with the controller prototype assembled on the breadboard before we install it in the case to make sure that all our wiring is correct while it's still easy to make any changes or fix any mistakes. We are not going to talk about network configuration in this video as we already covered that in the last 2 videos. For this video, we'll focus on the specific settings in the config_buttons.h sketch we need to configure for our new hardware. We'll work on configuring settings for the rotary encoder, the keypad, OLED display, additional buttons, and battery. So we'll open up our WiTController code in the Arduino IDE and find the tab for the config_buttons.h sketch. We're only going to look at the configuration settings we need for the hardware we assembled in this video. See part 3 of my last video, number 9B, using WiTController with DCC-EX for information about the other configuration variables. Rotary encoder. First, we'll decide which way we want to rotate the encoder knob to increase the speed. I prefer clockwise, so I set the encoder rotation clockwise is increased speed configuration variable to true. Next, we can set the debounce for the rotary encoder dial and button. I found that for the dial, setting the rotary encoder steps variable to 4 works best, but we can experiment with smaller values. I've also set the rotary encoder debounce time variable to 400 for the push button. Again, we can experiment with other values. The rotary encoder on the OLED encoder combination board we've used in this video is a bare EC11 encoder and not a KY040 module, so we need to set the EC11 pull-ups required variable to true. Later, we'll find the speed step variable where we can set how many speed steps each turn of the encoder increases or decreases the speed. Keypad functions. Next, we'll configure our new keypad. We do this in a few different places. The first thing we need to configure is which action or function each key performs. Remember, we can see a list of all the available actions in the actions.h sketch. For this example, I've set all the keypad keys to activate DCC decoder functions, except for one key I've configured to be the emergency stop and another to switch to the next throttle. Next, we enter the names we want the WiTController to display on the OLED screen for each of those keys. Note that we cannot change the actions associated with the star asterisk or the pound hashtag keys, but we can decide which buttons on the keypad to assign those keys to. We can also set the hash shows functions instead of key defs variable to true to automatically turn on the shortcut that allows us to press the pound hashtag key to set our locomotive's other DCC decoder functions. We can also set the number of throttles we want our WiTController to have when it boots up. The maximum is 6. Next is the speed step variable I mentioned previously. The default is 4. I always change this to 1, but then again I always run my locomotives at low speeds. OLED display. Let's scroll down now and find the configuration variable for the OLED display definition. I actually have 2 of these OLED encoder combo modules, and even though they look identical, each one uses a different definition. So if the first one you try doesn't look right, try the other and see if it looks better. Keypad hardware. Now we'll define the keypad hardware. We'll make sure to configure a 4x4 keypad. As I mentioned earlier in the video, since we are not constrained by the keypad, we can assign the keys to the buttons however we like. In this case, I've arranged the keys for the numbers 4 across with 0 to 3 in the top row, 4 to 7 under that, 8, 9, and A and B keys next, and the star asterisk key, C and D keys, and the pound hashtag key in the bottom row. I've kept the default pin assignments. We can also set some keypad debounce and hold time if the keys seem a little twitchy. Additional buttons. Now we can configure the 2 additional buttons that are on the OLED encoder combo module. We'll need to set the Use New Additional Buttons format variable to true. Then we can set the New Max Additional Buttons to 2. Next, we list the actions for our 2 new buttons. Because I typically run my locomotives at very low speeds, I like to have buttons to increase or decrease the speed by 1 speed step, so I set these buttons to perform the speed up and speed down actions. Again, we can find all of the available actions in the actions.h sketch. If we want our additional buttons to activate DCC decoder functions, we also need to indicate whether these should be latching functions like the headlight or momentary functions like the horn. Set the New Additional Button Latching values to true for each latching button and false for each momentary button. The setting has no effect on actions that aren't DCC decoder functions. Next, we assign pins for each of the buttons. Here, I've assigned the Speed Down button to pin 26 and the Speed Up button to pin 27. Finally, we need to specify whether we are using the ESP32's internal pull-up resistors. The combo module I am using has external pull-up resistors, so I've set the values for these two buttons to input. You may need to use the input pull-up setting if your board doesn't have pull-up resistors for those buttons or if they don't seem to be working properly. Battery. Lastly, we can configure our LiPo battery settings. If we've wired up the voltage divider resistors, we can set the Use Battery Test variable to true and set the battery test pin to the pin we are using to measure the battery voltage, pin 34 typically. To set the battery conversion factor, we check the serial port monitor for a message about what the conversion factor should be. We'll need to make sure that the battery is fully charged when we do this. If we have installed a switch for the battery, as I have in this example, we will need to make sure that the switch is on when we want to charge the battery from the USB cable. We can put the WiTController to sleep if we are not using it by pressing the ** key to enter the main menu, 9 to enter the extras menu, and then 7 for off sleep. We can also decide whether to show the battery percentage on the OLED display and whether the WiTController should go to sleep when the battery gets low. Set the Use Battery Sleep at % variable to 0 to prevent the WiTController from shutting down when the battery is low. We have now configured all the hardware settings for our new Candy Bar WiTController. Part 3. Let's run some trains. Now that we have assembled and configured our new WiTController, let's go run some trains. We'll turn the WiTController on, connect it to our command station, select a locomotive or two, and we're ready to roll. We can activate our locomotive features, set some turnouts or a route, and get to work hauling freight. All aboard! Finally, long-term viewers may remember that in my first video, I mentioned that from time to time I would highlight some of the model railroaders here on YouTube that inspired me to start this YouTube channel. So before I go, there is another model railroader here on YouTube that I'd like to highlight.
Let's create the IOTT, the Internet of Toy Trains.
If you enjoy the videos that I produce on this channel, then you should know who Hans Tanner is. A longtime model railroader, Hans is best known today for his YouTube channel, The Internet of Toy Trains, or IOTT.
Hello YouTubers and welcome to the Internet of Toy Trains. I'm Hans Tanner and here is a new episode of IOTT.
Hans has been building his own model railroad electronics for over 50 years since he built a homemade block signaling system for a friend's model railroad in 1975.
Some copper pieces served as contacts to make an SPDT relay, which then was used on my neighbor friend's model railroad layout to implement a read contact activated block signal system.
In 1990, Hans began working with Markland's Motorola-based digital command system, and after trying it out, then built his own decoders and command station to learn the details of its inner workings. When Lenz released a system that the NMRA would adopt for its DCC standard, Hans began working with that. See my video number 4X, Assembling and Configuring a DCC-EX Command Station, bonus materials for a brief history of DCC. When Microsoft released Windows 3.1, Hans decided to take up the challenge of writing a Windows-based model railroad control program, and in 1992 released his Winloc model railroad control software. When Digitrax introduced its LocalNet system, Hans added LocalNet support to Winloc. Hans also developed the freeware decoder programming software that Digitrax bundled with his DCC decoder programmer, the PR1. In 1998, the new Putra Kelana Jaya rail line in Kuala Lumpur, Malaysia, A fully automated, driverless, light rail passenger system built a Digitrax-based HO-scale model railroad to train its dispatchers. The layout used WinLog 2.1 running on a Windows 98 PC to operate the trains, turnouts, signals, and to use the feedback from the block detectors for train control. Hans configured and programmed all the equipment to Putra's specifications.
One of the questions I hear once in a while is, why do you make everything open source?
A fierce proponent of the open source movement, Hans was caught up in the lawsuit against JMRI and Bob Jacobson that I described in my video number 5A, An Introduction to JMRI. After JMRI's competitor obtained patents on Hans and others' technologies, the competitor sued Hans for patent infringement. Hans was able to show that the patented technologies had been in prior use for years, ultimately resulting in the JMRI competitor dropping the lawsuit against Hans. Hans also provided testimony in the various lawsuits between the JMRI competitor and Bob Jacobson, and the JMRI competitor eventually disclaimed 2 of the patents and settled with Jacobson. Hans started his YouTube channel in 2018 after a near-death experience. Since then, Hans has been a prolific tinkerer and designer of a family of electronic model railroad accessories for LocoNet and DCC-EX systems, which he makes available on his GitHub page. Hans also operates a Tindy store where he sells assembled versions of some of the products that he has designed. Unfortunately, making YouTube videos and running a Tindy store takes a lot of time and effort, and Hans has had to slow down a bit in the past year due to some health complications and a move to a new state, among other factors. However, slowing down on making videos and running a store does not mean that Hans doesn't have a long list of projects that he is in the middle of.
As for now, here is the list of projects I am working on and plan to publish some videos about.
In addition to working on his G-scale garden layout, Hans is working on a new locomotive decoder that incorporates a train speed measuring system, a low-cost DCC turnout decoder, a new time-of-flight block detection sensor, and a new DCC command station integrated with a large rotary knob and touchscreen display. And echoing Hans' very first video on the channel, he is still looking at how to integrate MQTT, Internet of Things protocols, into model railroading to do things like allow the command station's fast clock to control the lighting in his layout room. If you haven't already, be sure to check out Hans' channel and look through some of his older videos.
Welcome to all new subscribers and welcome back to everyone else. I am happy you made it here and thank you for your continued interest in my channel.
I, for one, can't wait to see what Hans comes up with next. What's next? Vibecode a throttle for DCC-EX. In my next video, we'll spend an afternoon vibe-coding our own DCC-EX throttle that we can use with either a wired serial connection or over Wi-Fi on a computer, smartphone, or tablet, including both iOS and Android. Be sure to subscribe to the channel so you don't miss any upcoming videos, and check this video's description for links to my other videos, including my video series on assembling a DCC-EX command station and my series on using JMRI's Decoder Pro app to control our trains. We finished our shuffle and cleared our dance card for today. Tomorrow they'll probably have us doing the hokey pokey. Put one car in, pull one car out, put one car in, and shake it all about. Until then, thanks for watching. Well, Scratchy, did you enjoy your day off? You're right, it never is enough. All aboard!